Everyone, I'm Won Lee. Today, I'm going to explain two-way ANOVA without replication. When you consider two factors, say temperature and pressure, you most use two-way ANOVA. Okay, let's review a little treatment effect and one-way ANOVA with treatment effect and sum of squares and degrees of freedom. Okay, let's see a little about them. Okay, here is one-way ANOVA model with treatment effect. Alpha I is a treatment effect here. And this is model, and they are two, not two, actually, they are K AIs, so K plus 1 parameters. Okay, so this one, Y double bar here, Y double bar is mean of total samples. So Y double bar is estimate of mu. Alpha I can be estimated by yi bar minus Y double bar. And this term called residual, realized value of error. So this equality holds. You move Y double bar to the left and square both sides and sum for I from 1 to k, j from 1 to n. Then the result is this formula. This is a sum of squares, and they are degrees of freedom corresponding to each sum of squares, right? Sum of squares is like this. This one, kn minus 1. This one, there are k terms here, and the k minus 1 and k times n minus 1. I explained those terms earlier. Now, we consider what? Two-way ANOVA without replications. Two-way ANOVA refers to a situation where there are two factors you're considering. For example, it involves testing hypothesis of whether experiment result vary based on temperature and pressure. They are temperature here, pressure. P level of temperature and Q level of pressure. They are PQ treatment in total, right? PQ treatment. These are each treatment, the result. In other words, you should say they are PQ populations. A key point to note here that when collecting data should ideally be obtained in a random order for PQ treatment population. So they are PQ treatment here, and you get only one observation. Then you get this means random order means you get observation A2 temperature and B2 temperature first here, and here A1 temperature, BQ pressure, you will get some observation. That is a random order, I mean. Remember the assumption of independent groups. When they are two factors, you need to differentiate between cases where each treatment has only one observation and where two or more observations are possible. So in this section, we just talk about without replication, only one observation case. Recall that in lab, obtaining one observation may sometimes require a significant amount of time and expenses. So it is pretty hard to get two or more observations. So in this case, without replication, the model and the hypothesis are Yij equal to mu plus alpha I, treatment effect of A, and beta j, treatment effect of factor b plus epsilon ij. The assumption is the same. There are two hypotheses, alpha 1 up to alpha p equal 0, no treatment effect for factor A. This one, no treatment effect for factor B. Okay, the equation obtained through samples for observed above two-way ANOVA model is like this. But here I write capital case letter Yij equal to Y double dot is estimator of mu. This one is estimator of alpha I. This part estimator of beta j. This one is for making equality. Yij is yi dot minus y dot j plus y dot dot. This one is y dot 1 is B's treatment mean. Okay, A's treatment mean, first level A1, that is mean is expressed y1 dot. It is my notation. Somebody may write down here y1 dot bar, something like that. But I use this notation for simplicity. Y dot dot is what? Grand mean, total mean of these samples. Okay? Understand that? All right. And same thing, same process applied here. Move y dot dot, move to left, and square all terms, and sum up I from 1 to p, j from 1 to q. The cross product terms here, okay, like this. How many? 1, 2, 3. So they are three cross product terms. Sum up. These cross product terms gonna be 0. It is amazing, interesting. Okay, so only these terms are left. We say total sum of square. This one is what? SSA. So A factor sum of squares. This one is B factor sum of square, SSB. This one is what? Residual sum of square. Somebody say error sum of square. There is no difference, I think. And degrees of freedom, PQ minus 1, P minus 1, because there is no J, so it is equal to Q times summation Y I dot minus Y dot dot square. So P minus 1, here Q minus 1, this one P minus 1, Q minus 1. It is pretty hard to find out this degrees of freedom, but for equality, PQ minus 1, okay? So P minus 1, Q minus 1, and this term is PQ minus P minus Q 1 plus 1. So equality holds for this degrees of freedom formula. Understand that? Okay, next, we have two-way ANOVA table without replication as follows. Sources, factor A, factor B, SSA, degrees of freedom P minus 1, SSA divided by P minus 1 is MSA, like this, okay? And residual SSE, degrees of freedom P minus 1 times Q minus 1, SSE divided by what? Divided by its degrees of freedom P minus 1, Q minus 1 is MSE, okay? The total, you don't have to worry about the total here. And F value will be MSA divided by MSE for factor A. In other words, for H0, alpha 1, alpha P equal to 0. For this null hypothesis, it is what? The value of test statistic. For H0, beta 1 up to beta Q equal to 0, the test statistic is going to be this, okay? So two F values appear. And of course, computer program calculate P value for this one, for this one. All right? Oh, here is the same table as before. Understand that? It is a little difficult or complicated, so you have to concentrate on this topic. Then many things will be easy to understand. Let me take a simple example, but I shortly just introduce. A factory decided to perform an analysis of variance to determine whether there are differences in assembly time based on four different assembly machines, A, B, C, D. Okay, the factory like to decide which assembly machine will be good. And there are six workers, six persons. To obtain the data, it is advisable to randomly assign each of six workers to machine A, B, C, D, and then measure of assembly time. The following is data obtained. What is randomization? They are person 1, 2, 3, 4, 5, 6. They are different person, so different skill level here. Workers skill level, concentration and personality and so on. So these persons are not identical. So you need randomize the order, machine order. For person 1, A, C, B, D assigned. For worker 2, D, C, A, B, randomly assigned to person 2, and so on. That is said randomization. Okay, let's see. It is anticipated that there will be differences in assembly time based on the skill level of the workers. Therefore, since the workers are treated as blocks, these are blocks. Okay, uh, blocks, and the machines are arranged in random order. It is also referred to as randomized block design. We call it randomized block design. Actually, this ANOVA, analysis of variance, is essential background of experiment design. Experiment design is another subject in statistics, okay, one semester course. But I just mentioned this kind of a terminology for you because you will study statistics longer beyond this level. Okay, the reason for blocking by worker is based on assumption that the assembly ability will vary due to the factors such as workers' skill level, concentration, and personality, that kind of reason. All right, I'd like to left the interpretation of this result tomorrow, next time. Okay, I hope you understand, you follow me very well, I hope. Okay, this is it today. Thank you, bye.